Okay, so here we're going to prove Rolle's theorem, and we're going to utilize the lemma that we just proved. So here's our lemma, and let's go through what Rolle's theorem says, and we'll see how it is that we use this lemma to prove Rolle's theorem. So firstly, let's read through exactly what Rolle's theorem states. So it says that f is a function that is continuous and differentiable on this closed interval. We could actually make it so it's differentiable only on the open interval, and Rolle's theorem will still apply, but, whatever. We'll just say it's continuous and differentiable on the closed interval, which is making this a slightly weaker statement than what Rolle's theorem actually says, but again, that's beside the point. Let's just say that it's continuous and differentiable on the closed interval. And we also have this condition that basically that at the endpoints of the interval, right, A and B, the function is equal. It's something like that. You have it where, this is going to be f of A, and it's also going to be equal to f of B. You'll have some statement like that. Now, with that being said, if that's the case, so far we've sketched it, then there must exist some point C in here where you're going to have it that the derivative is 0. You'll have some point. That's guaranteed to exist. There could be more than one C, but it's guaranteed that the slope of the tangent line at some point is going to be 0. Proving this, again, you use this lemma here. So let's go through this proof in a rigorous way. So we know f is going to have f of A equal f of B. So f may attain a minimum on AB. Okay, so what are the cases? F attains a min at some C contained in A comma B. In the closed interval, F attains a min at some point other than A and B, right? So its min value is at some point other than A and B. And if that's the case, right, if f attains a minimum at some point, then by lemma, f prime of C will equal 0. And that's one case, right? So f could attain a minimum, some minimum, it doesn't matter. It could also attain a maximum, but it could, if it just attains a minimum and it doesn't attain a maximum on the open interval, then if you look at the lemma, then everything is satisfied. So f will attain its max. If f attains its max or min at some C, then we know the derivative is 0. So one possible case is that f attains a minimum. Now, f might not attain a minimum, right? But let's say that f attains a max, and for the same reason, right, f attains a max, right, at some C contained in the open interval, then again by lemma, f prime of C equals 0, and then there's some C that is guaranteed. So now we have it where f attains some min, f attains some max. Now the only other option would be that f doesn't attain a min and f doesn't attain a max. This is if f attains any min, then you know by the lemma that at that point the derivative will be 0. F attains any max, then you know at that point the derivative will be 0. Now the only other case is f does not attain max or min on the open interval A comma B. Okay? If this is true, then what must occur is that then f is constant on A comma B, and the derivative of a constant is 0 everywhere. For every C is it true, then this is the case. So in all of these possible cases, right, these are 3 different cases, and every single f that meets these conditions, right, will fall into one of these 3 situations: this first one, this one, or this one. And in all three cases, there's always some c where the derivative is 0. The last case, let's just go through and just make sure it makes sense again. So f does not attain a max or min on this here, right? Then f must be constant, right? We have it that f of a is equal to f of b, right? So like if it went like this, then f would not attain its min or max on this open interval, right? Its min would be at a and its max would be at b. But since we have this added condition of f of a equaling f of b, it must be the case that it just goes straight across. If I could draw a straight line. Okay, it must be that it just goes straight across, in which case the derivative is 0 everywhere, and that this is still satisfied, and Rolle's theorem is still true. And those are the three cases, and you should convince yourself that every case of f fits into one of these three cases, and that this last case, how it will look if f does not attain its min or max on this closed interval, and where you can't apply this lemma here.